我们开始上课啊。So 2 weeks before, 2 weeks ago, we mainly talked about the properties. In particular, we try to use the contour integral to systematically define or represent different kinds of properties. And among them, there will be a particularly important one. We will use it quite often later in this course, which is the so-called Feynman property, known as EF smash R. And we saw in our lecture, this is defined as with time ordering, okay? Time ordering proof of function. And it can be very simply represented by a contour integral. Or in momentum space, it can also be simply represented by some I epsilon prediction. So there are many ways to talk about it. Yeah, which is the Feynman property. Some of you may wondering. Yeah, so this is basically defined as T Y. Yeah, sometimes we just think or we already thought this property is particular physical property. You may ask why. We also know there are 3 different kinds, right? So why this is special? So if you think about it carefully, this time ordering makes this propagator particularly physical. Essentially means the initial operator, which is earlier time, okay? Which take the responsibility to create a particle, right? Will be always in the right. So this time ordering guarantees if the earlier operator or the initial operator, okay, will always create the particle and then annihilate it. Okay. So in that sense, this is physical, not the other way around. As we discussed in great detail 2 weeks ago, there are many different kinds of proof functions. You have to distinguish them carefully. For instance, if you're talking about the Feynman function, just some overlap, it's not that quite physical. But for this one, we really interpret the initial operator or initial state was created and then animated. Depending on which operator carries the early task. Okay. In that sense, this is more physical. So they also talk about the interacting theory, introduce the interacting theory, and related to the experiment, and define the so-called S matrix. Try to relate what we discussed so far to the real experiment. The key point is the easy way. First of all, S matrix itself is quite simply can be defined. Just assume we will define the asymptotic states, initial state and the final state, which are free all interactions. Okay. So again, there's one more remark for this assumption. It's not always true. For any given theory, you can make this assumption. It's not always true. We don't want to push much into details along this way, but there are some theorems that if the theory has a mass gap, you can always make the initial state and the final state far away from each other in time direction. Or also space direction, you can always create some asymptotic states, well-defined asymptotic state, free of interactions. But the point is that assumption is not always true. Some very particular series, special series, there may not exist such kind of asymptotic state. Then S matrix is not very defined. It's possible. It's not always true. But here, in order to define this, we know this is the biggest. This is the important assumption. And we also just show without proof and leave you as homework to try to prove the so-called RSD relation, which essentially relate the correlative function time order one. Again, time order one. See, only the time order one can be directly related to the X matrix entity. But the reason essentially I just explained, because the time order one is really physically restricted. Guarantee that the initial state was always created before, then and then later. Right? Otherwise, you somehow violate the causality. Right? It's quite unnatural, right? Your late time operator, or late time state somehow create the alternative. That's weird. Right? Yeah, I'm not saying that all other propagators are useless. Okay, I'm just saying this one is more directly related to the observers. Okay, in this context. For instance, some other propagators might be quite useful in some other context, like the Condon's matter fields, or some other non-equivalent system. But it's just a comment. So today, of course, we will continue to push this game. Meaning that we know LSD demand that we have to first compute the time order correlative, and then by this formula we get the S matrix element. So how to do that in practice? It requires us to first compute the time order correlative explicitly for interaction theory. Yeah, that's the next step. We also mentioned last time the quantization condition for interacting theory. Yeah, so we'll continue to discuss the interacting theory. The quantization condition is expected to be still true. Namely, the commutation relations between the fields and between the field and his conjugate counterpart. Those commutation relations expected to be still true. So the job is going to compute something like this. Okay? Say I will use X and S prime to denote these two space-time points, and with the time ordering, and averaged by this the state. Now I call this omega as the new vacuum for the interacting theory. In principle, the vacuum for interacting theory could be different from the vacuum for free theory. Okay, free theory is quite trivial. The interacting theory can be complicated. Yeah, so how to compute this one? How to compute? Yeah, so obviously, so since we're talking about interacting theory, we saw already the complex from last lecture. If there are interacting theory, so many things are changed. Okay, so if you want to compute this one, it's not an easy job. So we decompose this into some small steps, and then try to finally solve this problem, at least to some extent. Okay. So what we do, we will first try to prove some very useful relations, and then try to use those relations, taking an example to illustrate how to compute this time order two-point function for a particular interacting theory. Okay? That's the strategy. So in order to compute this one for an interacting theory, it's useful to first prove or first show the following relations. Relation is going to be a little bit complicated form, but it can be easily used. Let me first write down this relation minus h bar delta four-dimensional delta function. This one. Okay. So you might just wonder why they want to just introduce another simple, more complicated object or equations to try to solve this one. Yeah, the difficulty is because of the interaction. Since there is an interaction, there is no simple way to, like what we did before, decompose either this operator or this operator, both of them, into some a diagram, and just using some simple commutation relation, you can get the result. It's not true. We choose using some other approach. So what is that approach? We try to use again. We try to use the method what we already used in the second lecture. We try to use the equation motion. In the quantum field theory, equation motion now can be promoted or can be understood as the operator equation. Okay, we try to use the operator equation to solve this problem. So this is one of the very important operator equation, as you can see. So what we do here is, the point is, even though I don't know how to directly solve this one, can compute this one, but I can try to think about it. If I act the operator on this one, what can I get? Okay? That's the idea. So if you try to act this box plus m square operator on this object, so what do you get? So clearly, there is a time order. Okay, the time order operation depends on time for sure, right? So it's not just trivially you can shift this operator inside. It's not true because t depends on time. Okay, you have to worry about whether this operation and this operation are commutative or not. Okay, so you can once you carefully take into account that issue and work it out, you realize that it's not simply just shift in, but there are some remaining terms. There's some remaining piece, which is a delta function. The delta function we know is important. There's a physical meaning for that, so you cannot simply ignore it. So we are trying to use this relation, but first of all, you have to convince yourself this is true, right? So we have to first show this one. So as you may already realize, this is very much like the exercise we did before, right? Last lecture, we tried to examine whether the time ordered or some propagator, whether it is a Green's function or not, right? Remember that? We tried to act precisely such an object on some two-point functions, right? And see whether I can get some equation like right-hand side, I can get a delta. You remember that? It's very similar to that exercise, okay? It's very similar to that exercise. So let's do it. So proof, since that's important, as you will soon realize, that's important. Let's try to spend a few minutes to prove it. Prove that equation. That equation is important. Okay. Let me see a few more words. So how to understand this equation is, let's say you can take a free field theory limit. Okay. You can just say, okay, you tell me some relation to true for interacting theory. I can view the free theory as some very special case of interacting theory. For instance, turn off my interaction, okay? Or just simply set such kind of all the things is for the free case, and what will happen? Then you immediately realize that if the theory is free, as we showed already last lecture, this will be equals to what? Zero. That's right. Because we what? Because we equation motion, right? Because we equation motion. So if the theory is free, this will be equal to zero. Okay. Now, since the theory is not free, this is not zero. Okay, anymore. Okay. I can check against the free field limit. If this is zero, then this is precisely their function. See? So this formula already also covered the fact in free case, a two-point function with time ordering is a Green's function. See? But now we want to really looking into the interacting theory, which essentially means this is not zero. This is essentially the reason to make this object complicated. You see, right? There is no more simple Green's function. There are something more, right? But for interacting theory, if you write down the equation of motion, this will be equal to some other powers of phi. Okay? Could be many different complicated powers of phi. So you see it? If then let's say I go a little bit more. If you replace for the interacting theory, if you replace this part by the equation of motion for interacting theory, then there will be a few phi's here. Okay, you can see it. Now this gives a relation about the two-point function and even higher, more points. You see, this means that it's complicated. Okay. But okay, we have a good sharp equation there. We will use it later, but first prove it. Just follow the step what we did last week. You can show this is true. For instance, this will be equals to if I take one's time derivative, okay, time derivative, then I will try to check how this time derivative passes through this time ordering operation, okay. Then as we already saw 2 weeks ago, there are step functions you have to worry about. So this is essentially the time derivative act on the one step function plus another step function with the xx prime reversed. Okay, so this is what you have to compute. Now, just do it straightforwardly. Then what you will get is this one. Plus some delta coming from the derivative taken for the step function. Yeah, you will get this one. See? Just do it straightforward. Okay? Now we have a delta function times this part. This delta function as a factor essentially means that this is only a non-trivial for t equals to t prime. Okay. If t equals to t prime, this commutator is essentially the equal time commuted, which is 0. Okay, by causality. This is 0. So this term is gone. Okay? This term is gone. Now we have to do a second derivative for this one. Okay? So the second derivative means we have to take in the derivative once more. Okay? So just follow the rules. Okay? You realize this working rule. If you take once derivative, meaning if you take a once time derivative for this part, okay, you again touch the same issue, pick up some delta functions. You see, the only difference is now the delta function. The delta function now is about there's the first term. There's the first term. First term we just acting once more time derivatives here. And plus delta function piece. Okay, the delta function piece now is about the together with this commutator. But now it's not phi x anymore, but its derivative. Okay, its derivative. So there is a partial t phi x commute with phi x prime. Just following the same steps as the last line. You get this one, right? Now this commutator again is also equal time for sure, but this commutator is no more the previous commutator, but it's the conjugate variable and phi. Okay? So by quantization condition, this is not 0. This is not 0, but this is the delta function. This is not 0, but the delta function. So you combine with this one-dimensional delta function, this is a three-dimensional delta function, combined together as we did the last time. So it becomes a four-dimensional delta function. So the final result we get is this one. I h bar delta 4 x minus x prime. Okay, so combine these two delta, we get a four-dimensional delta function, and this is the first piece, and this is the final result. For what? For this second time derivative acting on this object. Okay, so why we care so much about second time derivative? Because if you look at the formula we want to prove, the time ordering is only about the time direction. Okay? Even though the box contains many other derivatives, but all the other derivatives, except for time, all commute with this t. Okay? Only the time derivative does not commute. You have to work it out. So that's why we carry through this time derivative calculation to get this one. As said, all other special derivatives just pass through this t, okay? Meaning that you can just shift it inside, acting on the phi, okay? So in this sense, we already proved this formula. We already proved this formula. Any question about this? The proof. I just show you the formula and show this is true. Okay? And this is true. I already explained that this just gives you some relations for interacting theory. Now, as already mentioned, you can check the relation. If the theory free, let's say that's below the free field the equation motion for the free field at some phi naught. Okay. This naught means the series free for the free field. Okay. Then this is the equation motion. Then this is the equation motion. Then the claimed this equation we claimed before simply becomes a Green's function equation. Now, since we let's simplify the notation, use just a simple df x prime. We rewrite this one. This will be the free case. Now, previously there is a h bar here. I just redefine. I can observe the h bar into this df. Get this equation. Okay, this equation we were very familiar. We already discussed it many times. This is a free series Feynman propagator equation. Okay? It satisfies the Green's function equation. So we can further simplify the notation. We don't want to this t too much, just simplify the notation without doing anything. We just relabel this interacting vacuum average for the t ordered something inside. We just break the notation. Simply use this bracket. Now, from now on, whenever I use such kind of bracket, it automatically means there is a time ordering operation inside. Okay? And it also means this is a vacuum average. This is average by vacuum. Okay? Clear? Now, this is just a feature. So, if we use this simple notation, and rewrite that equation will just become 5x box plus m squared 5x x bar minus I h bar. Right? Just rewrite it. Using this simplified notation. Okay? Essentially means this box operator you can shift it in with the payment that the delta function appears. Okay? You created a delta function by shifting the box into this two-point function. Okay? Also, we always using the notation that whenever I just write this box means the operator for the x position. Okay? X prime. Okay, clarify. Now, so we already proved this one, but now we want to generalize a little bit. Later, we will use a more general formula similar to this one, but not precisely this one. But a generalized one. Generalized form. We are not going to prove, but again, give you exercise. Prove it. But it can be naturally understood to be correct, which is the box again, ix. So that's only about the two-point function, okay? As we saw last time, by LSD formula, in order to compute the asymmetric element, we might need many points insertions, right? Many points for any function. Depends on you, what are the total numbers with this in and out, coming and out particles, right? Random numbers. So what if, for that kind of relation, what if there are many insertions inside? Say, for example, I have so many n plus 1 actually point functions if I act by this one, now I even brief the notation. I just throw away the m squared. Well, you can think that this is, I just redefine the box x by including the m squared. That's fine. I just want to simplify the notation as much as I can. Okay? Because there are many long, very long equations. So what if you try to compute this one? Now just following that rule, you can expect the first term will be the box was shifted inside, okay? Without changing anything else, okay? That's the first term. Clear? Of course, this is the term you should expect, right? And there could be many other terms. That's the point, right? Now, in the case of two-point function, the only remaining term becomes the delta. So you can roughly think the remaining terms is just about see, there is an x prime here, right? Okay. The remaining terms are about depends on how many remaining insertions here. Okay? If there's only one insertion x prime, see, at x prime, then you just kill that phi x prime, kill that, but replace it by a delta function. See, delta function is about the x minus x prime. You see, I'm trying to generalize the rule. Even though this is a simple two-point function, I'm trying to guess what happened for many. Okay. Then the natural guess, the remaining term will be again h bar, and then there is a sum. There is a sum depends on how many other insertions you have. Okay. If you have a single one, you will just have their function. But now you could have many. So what could be the most general terms here? I can write in this way: y x1 y x j minus 1 y x j plus 1. We clear? See, it's just about you erase. Okay, you erase. Of course, you will not have phi x anymore. But even for the remaining terms, okay, the contribution will become just from the experience of the two-point function case. It's about to just erase the particular insertion xj. Okay. Okay, and replace it by times a delta function about x minus xj. You just erase the j's position. You see, j's insertion. But if you have more than that, then you should keep the other insertions. Okay. The point is, you should sum all over the possible insertions. Okay. About the j. Okay. This is the most general one. For the multiple insertions act by this operator, what do we have? This is the generalized formula. Do you have any questions? I'm not going to prove it, but you can easily. There's no difference about that one. I just follow that rule. Compute it, okay? You can get it. Compute it, you can get it. At least you can see, right? This is really the generalization of the two-point function case. Now let's consider a particular theory and try to perform the real calculation, meaning try to take use of this relation. And try to do an exercise explicitly to compute the time order formula for inequality theory. Now consider a theory. Which kind of theory? Let's take the the simplest non-trivial interacting theory, okay? Which is the 5 to the qubit theory. This is the free part. We write many times. Now, I'm going to add this interaction term. I'm going to add this interaction term. So formally, this can be many different kinds, right? The point is, if we keep it in the most general way, with this interaction term, the equation of motion, you can work it out to be the box plus m squared phi minus L interact derivative with respect to phi equals to 0. Okay? As we introduced a little bit last time. This will be the new equation of motion for the interacting theory. Depends which kind of interaction you add to your Lagrange. Okay? Sometimes I write the Lagrange, the free part of the Lagrange in this way, but it doesn't matter, right? Up to total derivative, as we derived a few times, up to total derivative, this is just the equivalent to the standard one. Okay? Standard partial phi square divided by the term. Okay? I just write it in this form, but it's just equivalent. Now you do variation principle, derive the equation of motion. It's not hard. Just realize this is the new equation of motion. This is again, this part is this term is the same as before. A new one is about this interacting term. Take the derivative with respect to phi. Okay. Remember that because you have to verify. Okay. For equation of motion, there are two terms. One term is the derivative with respect to partial phi. The other term is the derivative with respect to phi, right? But the point is, this interacting term, we only consider it a function of phi itself, not derivative. Okay? So they only contribute in this way into the equation of motion. Okay? This is the new equation of motion. Now, of course, you realize what I want to do. As already mentioned a few minutes ago, we want to insert this new equation of motion, treat this as an operator equation. We want to insert this equation to insert to here, to replace this term. Okay. We want to replace that box phi by this new term, which depends on the interaction. You see? Because we know in quantum field theory, the equation of motion becomes the operator equation. Clear? If you have some well-defined operator equation, you can basically use it almost everywhere. Okay, almost everywhere, because I have an operator equation. If that's operator equation, it just means it's like in quantum mechanics that we have a operator equation, which is about the matrix equation. It doesn't matter averaged by which kind of state is always true. Okay, that means operator equation. Is that clear? Operator equation. If you have an operator equation, okay, it's like a conservation law, meaning that doesn't matter which kind of state you use it to average that operator. Okay, or even with some other operator insertions in the correlation function, you can still use it. Okay, that's the point. That's what we mean by operator equation. So we promote this exercise in an operator equation. Since we discussed a lot about free theory in previous few weeks, but now we are moving to the interacting case. But this kind of basic concept doesn't change, okay? As we saw for the quantization condition, okay? Some principal conditions do not change. It doesn't matter for free or interacting, okay? This equation of motion as an operator equation is also true, even for interacting theory. So this means what? This means I can just I can just replace this term as that. I just brief this box to carry M squared. That doesn't really matter. The point is I can replace here by the L directing partial part. Just use equation motion to see and use this, and I get that one. Okay. So this is the equation we finally arrive. Still, this is the preparation for our computation. We didn't really discuss the application for this equation. But at this moment, we just build up some equations, which is very important. There's even a name for this equation. This is the so-called Schwinger-Dyson. Schwinger-Dyson equation. Just this equation. Okay. We didn't use anything. We just used the quantization condition and the equation motion. But both quantization, the condition, and the equation motion are exact one. We didn't even propose to expand anything. See, up to now, all the equation is exact equation. Okay. As we will soon realize, to exactly solve our interacting theory is extremely hard. And mostly we just do some perturbative expansion. But the point is, up to the step we obtain the Schwinger-Dyson equation, everything is non-perturbative. It's no perturbative expansion, or everything is exact. Okay? So that's why Schwinger-Dyson calculation is very important in quantum field theory, because it does not depend on the perturbative expansion. It's completely non-perturbative. Okay? So that's the power of Schwinger-Dyson. Yeah, we can spend many hours talk about Schwinger-Dyson, but we don't want to do that. We just try to build up this equation to finally compute the object we are interested in. And it's just as a remark. Schwinger-Dyson is an important equation to solve some non-perturbative problems. So, yeah, we will just continue. We didn't finish yet at all. We just want to continue. Up to now, we obtained this for Schwinger-Dyson. Now we will try to take use of this equation to compute the object. True task we want to solve. To solve this one, to solve the initial goal, we further simplify the notation. We are just using this subscript phi x to denote some phi x, okay, and phi j to denote some phi xj. Okay, and delta xi, just relabel a few complicated objects. Yeah, I just try to make all the variables into the subscript, such kind of things. I just use delta xi, but truly means this fundamental delta function. And even for the propagator, see, I use dij or dji, but as we mentioned last time already, if there is a time ordering in the definition of such kind of D propagator, okay. Okay, yeah, that doesn't matter. It doesn't matter. This is defined as df xi xj. It doesn't matter ij or ji, right? You see, because at time order, depends on your explicit location. If you give me the explicit insertions, which one has the earlier time, which one will be staying right. So you are free to say okay, dij or dji. Doesn't matter. So I just use that kind of super simple notation to denote such kind of object. Then in this further simplified notation, you can see the Green's function for D will become also so super simple. Okay, box X act on D X C I will be equals to minus I delta x 1. You see? This is the Green's function equation, you see? Using my new notation, super simplified notation. This will be the Green's function equation. Okay? Now let's play some game or some very easy game. Let's consider a very simple two-point function, phi1 and phi2. You see? Now, after introducing such kind of super simple notation, you can understand this kind of object actually means phi x1, phi x2, okay? Time ordered, okay? And averaged by the interacting theory vacuum. That's the full meaning of such simple objects. I can use the trick, what you learned in your second year undergraduate course. I can rewrite this object by using a dirt function insertion. Essentially means I can replace the phi1, okay, by a delta x1. And after that dirt function, and I do integral over x. That's almost the definition of dirt function. You remember that? Dirt function is defined by integral, right? Dirt function is defined by integral. Dirt function pick up. So from right to left, you can see dirt function pick up. It basically set x equals to 1. So it pick up x equals to 1 contribution and clear this integral. Okay? So right really equals to the left. But I can always rewrite it. It's just a trick. You should agree with this one, right? This is the definition of dirt function. So what is this? Now I'm just trying to step by step try to take use of what we already derived before, already have before. So since you have such kind of equation, okay, you can observe that I also have a delta x1. You have a delta x1 here, and I can replace further this delta x1 by this left. Okay, I just try to play some games. Okay, so this will be equals to I dx force box x e x1 with phi x and phi 2. You should agree again, also with this equation, right? But I just take use of this one. Okay. Take use of this one. Take use of this one means what? It means this is the free case for free theory. I'm now just trying to check a two-point function. Sorry, maybe me confuse you a little bit. I'm now consider the free case, free field theory, which means for this average, you should think about the average by the free theory vacuum, which is 0. Okay, we used it before, and that's try to play the game to first replace the dirt function insertion together with the integral, and then try to use the Green's function to replace the dirt function. I get this back box back on D, and I can perform this calculation further then I can get delta. I can try to shift this box. When I set up to a total derivative, you can always do this. I can shift this box to the later part. So I will get dx1 box x acting on phi x and phi 2. Okay? Up to the derivative, you can do this one. Now, as said, we are working on free case. If the series is free, essentially means the box x acting on phi x dot 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 or phi y, okay, or phi 2. So this part for free series, this part will be equals to minus phi delta x2. You agree? Right? I just did nothing, but just repeat try to use whatever I can have. Now, since you have this one, I realized, okay, this is nothing but if the series is free, just a 2-point function acting by box. You already told me that such kind of 2-point function is for the free series, then you automatically can take use of the green function equation. Again, this becomes the delta. So this will be equals to integral x4 dx1 delta x2. Delta x2, okay? And you can check that, of course, you have a delta function here with the integral, then this is nothing but the d21 or d12, that's the same. Okay? So indeed, this is just about a consistent check. Indeed, this agree with the initial definition, which is d12. See? So just playing some games to try to check, okay, using this funny super simplified notation and use the trick of what we know, I can check really the consistency. I start from here, blah, 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 blah. Eventually, I check, okay, indeed, this is d12, okay? Because the series is free, this is just many equations, just the trivial. Now, we also know, keep in mind that the really difficult task is about the interacting case. But it's worth to just check consistency to get familiar with this game, okay? Even for free case, just play with the game. We are going to play this game a lot, so it's worth to get familiar for the trivial case. So this is about 4 points. You see, this is about 2 points. What about 4 points? Again, even for a free case, let's check a 4-point function. We show some equations about higher insertions, right? Many operators, not only 2. But what if there is a 4? So if I have 4 insertions, meaning that phi 1, phi 2, phi 3, phi 4, this case, then again, I can try to play the game. For example, I can first try to replace phi 1 by acting on a box with an integral over x. Okay? Now I jump a little bit. For this formula, for this equality, I jump a little bit. I just find one step to take use of something we derived here. You see, something we derived here, right? You see, here we claimed you can always get this one equals to this one. Okay, this means what? This means you replace one particular insertion, in this case is phi 1, by some phi x. The payment is you act a box in front, together with a dx1, and then together with the integral over x. Okay? Even though it's quite trivial, but you know, it's interesting. It's cute game. I just take use of this equality. I can write this one. Now if I have this one, I can now try to follow Schwinger-Dyson. If you're following Schwinger-Dyson, what do you have? You will have this one, x1. Okay, as Schwinger-Dyson found, as this equation claimed, you see. Now I'm trying to play the game for the higher point insertions, which is a 4-point function. But now I don't want to complex the job too much. I want to first restrict to the free case even, which means for the Schwinger-Dyson equation, this term becomes trivial. You see, but this sum is not trivial. You see, there's a sum. There's a sum here. The sum essentially depends on if you have higher points, then you have many sums. Now I'm just trying to take use of that one. Okay, even in the free case, there is non-trivial sum. So there are many pieces. I just write the sum explicitly. What I have is this one, delta 3, I2, I4, plus delta x4, I2, I3. Is that clear? Because this sum is essentially say, whenever you erase which particular insertion, you have to pay the delta function in front. Okay? See? That's about the sum. Okay? It's precisely this way. Because the box is on phi x, we don't care phi x anymore. Now there are remaining 3 insertions. Okay? And let's do one by one. For the phi 2, if I erase the phi 2, you see I already erased the phi 2. The payment is there is a delta x2. You see? There's a delta x2. There's delta x2 here. And if I erase the phi 3, there's a delta x3. If I erase phi 4, there's a delta x4. Okay. This is the reason how these 3 terms come out. Okay. Now, because of this one, now you can easily check that this is simply nothing but what? If in free case. This is D34, right? So this is D34. Now you realize this is the D34 now, and what is this? You see this delta function combined with this integral over x, you just pick up set x equals to 2. And there's another D12 in front. You see? Now realize that this is a simple fact. You can just work it out. The result tells you that this is nothing but D12 times D34, and the second term D13 times D24 plus D14 times D23. Okay. Is that okay? So you see, it's interesting, right? Even though it's free theory, we can just play some exercise to work out the 4-point function. Indeed, because of the fact that theory is free, you can do this explicitly, get the exact result. Meaning that we can, let's say, intuitively, this essentially means that in free theory, 4-point function or any higher point function eventually will be factorized into 2 points. Okay, because there's no way to create more interactions, do more contractions. The only possible way, you have many points. The only possible way to contribute the entire correlation function is about to pair all the points, okay? Because the only contribution is a free propagator. That's the point. It cannot be an interacting vortex or something like that, okay? The only way is just to connect. See, I have 4 points, so just to connect 1, 2, 3, 4. This structure essentially means what are the different ways to pair them, right? To pair the 4 points. You see, to pair or in this way, 1, 2, 3, 4, or 1, 3, 2, 4, or 1, 4, 2, 3. So you can picture-wise to illustrate what I just said. This is nothing but you can picture-wise this result in this way. So this is 1, 2, 3, 4 plus 1, 3, 2, 4 plus 1, 4, 2, 3. Okay? This is what I mean. Okay? If you want, what about the 4 points? 4 points, this kind of thing is just, you know, if you want to compute this one, you can just do it this way. Use a bracket. Okay? This is the picture-wise object you want to compute. Okay? Now, what is the result? The result is goes in this way. Because the series is free. Only the 2-point probability can contribute. So this is the result. And this is exact. But so far, it's, again, we are still in this trivial series limit, trivial series size. We haven't really go to the interaction case. So what will happen to the interaction case? So now, two jobs will turn on interaction. Turn on interaction means that we turn on this interacting, they will interact. For example, I can consider this L interact, the particular series, which is a set with I cubic. Let's consider one power higher than quadratic, okay, which is 5 to the cubic. Okay. Let's define the interacting part in the Lagrangian in this way. This is the so-called G is so-called coupling. Okay. Coupling delay, coupling is prepared for the interaction. Coupling the interactions process. Now this is the 3 factorial. We will explain why we prepare such a fancy factor here. We will soon explain that. And then this is factor. Now, what if the series now really becomes interacting? As emphasized many times, this just simply means the some of the steps for the free series doesn't work, right? In particular, those steps, if you're trying to use the Schwinger-Dyson, if you're now trying to use Schwinger-Dyson, meaning that you try to shift the box operator into the correlation function, you cannot simply forget about this first term in the right-hand side, which is this term. This is the key. This is the key difference. Yeah, this term is the key difference. If we're now contribute the case of interaction. So what? So now if I want to now recalculate now, remember that I don't specify using notation to distinguish interacting free, but now I'm working on the interacting series tree. Now again, if I want to use some of the trick I used it before, for example, I just try to replace this one replace this 2-point function. What is the game? Sorry, this one. This is the equation I want to follow or repeat, recalculate. If I try to take use of this result, I have to be careful. See, this step to this step is still true. It's nothing but a delta function insertion. This step to this step, is it true? And this step to this step, what about this step to this step?
That step is not true. The first one. You have to have a interaction.
Yes. So, as I said, this is true, right? Now, we use this one to exchange this one, so this is not true. We have to rewrite this one, and eventually, after total derivative, rewrite this again to go further this form. And certainly, this form is also not true. So you have to rework in this case. So after a few calculations, you realize that indeed there is a new result compared with free case. You get something like this. Previously, we said in the free case, one can simply get finally the result where D can be equal, right, as the D, right? D together with the delta, right? Now it's this part. There is an additional contribution, essentially because of the interacting. Here, okay? And in particular, this term comes from the box phi, okay? So how to get this term? This term comes from box phi, and furthermore, because of the derivative taken with respect to phi, comes into the equation of motion from the right hand side. That this will be equals to, take one's derivative will be equals to g over 2 phi squared. See? So this is a new term in the case of interacting. And the phi x, now you may ask me why there is a phi x squared. So what is the meaning of this phi x squared? This needs a little bit caution. This phi x squared means there's a local operator, but you take square of that local operator. Okay? Okay? That's the meaning of this phi x squared. So how it comes? Essentially because there is even in equation motion, you have such kind of structure. And if phi is a local operator, you take the square, then you immediately get the stacked one, right? Not only hold phi, but you take the operator square at the same point. At the same point. It's not a big deal, right? You can understand it. If the operator itself is well defined, for instance, in quantum mechanics, in quantum metrics, you can just take square. Or you can take multiply two measures. It's okay, right? It's okay to understand. So you get this result because of this error interaction. Now I can write this as d12 minus t. I just shift this term in front. Because this term combined with this term, as said, it simply becomes d12, right? Yeah, this is correct. But you should remember now I further use the trick to perform this trick, and this is the dx1, dy2, box y, ix squared. The second term I can write in this way. You see, for this step, but from here to here, I just do the trick once again. I just do the trick once again. But now for the phi 2, okay? As said, you can replace phi 2 by another phi y. The payment is acting on box y. Now together with the dy2, but now integrate over dy1. I can get this one. Now just compute this one straightforwardly. This is d12 minus t squared dx1 d2y yx squared y squared plus y g dx 1x 2x yx. Now, what we do here, you see, for this step, I just reuse the equation of motion. Because equation of motion doesn't care, it's interactive free. To replace this box acting on phi y, phi y squared. You see? Now you keep going, you will, I jump a little bit for some steps, but you can check. Just using the rules, you can finally get this one. Now what we do? Up to now, we just try to use this replacement rules, try to rewrite this two-point function. We don't do anything, right? And now up to this term, now since I get a g squared, now I will use some approximation instead to get an exact result for interacting theory. It's very complicated. But the trick we can do is after you get some terms, I can do some approximation. For instance, in this case, if I get a g squared, if g is small, I can approximate this term by the free result. Because I only want to care the result up to the g square order. Okay? If I want to care up to the g square order, I can approximate this one by the free field result. Free field result. Is that clear? You have an interacting theory, you have some coupling G. If G is small, if you really try to solve this one together with the coupling, okay, then you will certainly contribute some more even higher G terms. You see, because this might include the leading order and some orders together with G, but you don't want higher orders. You want to stop to G square order, meaning that you can approximate this kind of object by the free result. Is that clear? That's the crucial step we want to take. Otherwise, you will not stop anywhere, okay? Otherwise, you will not stop. You can always do this expansion, then you get infinite terms, okay? But we don't want to do that. We want to stop at some point. What is the rule for that stop, as just explained? If I have such kind of structure together with some G squared term, if I want to stop at the G square order for any term, for all the terms. So whenever I have such an term, I can simply replace this one by free result. Okay. And yeah, we are going to do a little bit more job to how to deal with this term. Maybe we can have a break and then continue. Yeah, yeah, 需要几分钟的去算。Now the point is here the E1 actually E1 is a free. This is we need to follow that rule. Try to write the interaction piece. Use of the phrase. Wherever I write P, I mean factorize. Yeah, sorry, I didn't emphasize. You see, I define the D this way. D doesn't mean this way. Okay? It's not this D.
对对上面的一是怎么的？这
一是 x 啊。dx 这个都是对比 cos 这个一，所以这个是 df 是我的例子是在保持例子 df 在yeah, it's just and now you need to work out. I speak to this again, you follow yeah, this is pretty confusing here. You got to raise this. Only in free cases is equal to D12. Okay. Now in the interacting case, you first insert replace by a direct function insertion, and then you try to just again reversely use Schwinger-Dyson. 这个也没问题，你就直接带它Schwinger-Dyson。Schwinger-Dyson 的话，这儿会变成这儿会变成 Where do I get it? Okay, there equals to Fox X on B. 还可以替换那个然后那个。我刚才说了一个 very function， 做一个我有 very function， 这个 function， 这个这个问题就是个 determination， 然后就可以直接做完了，可以。正常的去。完了啊。
好像就是 interaction theory 的话，还是是吧？就是方起来的这个发生，然后
we use the current function interact. Current function interact with knowledge. 肯定不能用 t 结束，你跟那个换的最后是要用 t。如果你把这个换成 interacting 的两点，叫用 d， 我在这里用 d 要 denote free。呀，我在这里显然是我跟 d label 的是这个 free， 所以直接这样写是不对的。interact
这里说开左上角，把它换成切温。
right。
好像看起来就是从这个地方去拍 Schwinger-Dyson。
就是你这个地方不用 d， 在做 interactive 的 d， 但是用它自己就去，是这个意思吗？所以这里我们要区分 d， 你只能考虑我们要区分 d 原来的 interacting 的两点函数。如果用 interacting 的两点函数是 OK 的吗？OK， 然后我在这儿的话，我们假设换一个 interacting 的，然后这个无论然后就 replace 这个by interacting。然后给了一个 high square。哦，第二个not precise match 什么？那个 B12 是 free 的，但是如果你这样做出来，好像有。
上次是不是你那从这个？哦，那是左上角那个。如果这个是啥？
我再看一下。
是，我就想到了，这个所以说就是变成这个一样的变成，对。这个题就是用这个意识自由场发生，就这传播自己发生，其实就是必须选自由场，结成一个指数的。这个括号是发散，或是自由场，啊，这个地方非自由场，对，这个就这里像说起来，知道这里听加了点，我就加了点，这边加，对。这个差，但这边下面展开之后，后面这个是自由场，就是它的自由场，那个小我展开之后，还是非自由场，应该是非就现在下面还只有那个要围绕需求底的时候，是吧？自由场做出来效果要更高级，所以这里面像。这个东西，那边就是自由市场，
这里有点不要格儿啥。 Oh, you go vacuum. Vacuum is defined as the lowest energy. It doesn't matter the phrase. Let's continue. So some of you might get confused. We're not super clear about the interacting case, how to get this result. Let's say this where this comes from. So if you repeat the steps here for interacting case, in particular this step is what do I mean by this step? This is still okay for interacting case if you insist this bracket is the interacting bracket. Okay, you see it? So it's correct or not correct. It depends on how you define this bracket. So it's still okay because delta function by definition is this one. Here I always using the D to denote the free two-point function. That's the point. Okay. Okay. So mathematically it's true, right? It's okay, even though I use some structure like a D in the interacting theory, but it's okay. Right? I just mathematically replace the delta function by this box D, by this equation. This equation is true. So when you do this replacement, keep in mind that D is again free theory result. So I emphasize here. Whenever I use D, I always mean free. Now, for that reason, you can safely replace it, but keep in mind that this bracket now is for the interacting. Okay. Now, of course, here is also for the interacting. Now, this step to this step is just the up to total derivative, exchange the order for this derivative acting. So of course, this is also okay. If you see this bracket is for the interacting case, this will be okay. Now, in the interacting case, box acting on 5. Now this step to this step is not okay. Okay. This to this is not okay. It's not okay. Now, for interacting case, box acting on 5 will be replaced by g over 2 by x squared. Okay? That's the equation of motion, new one. Okay? This is where this term comes from. that clear? Right? Now, then this step to this step, as explained, this is D. This term gives the D12. Again, this is free. You see? You see the reason, right? The free result comes as some kind of leading term, essentially because we replaced by the delta function by a mathematical green function equation. Okay? We use a free propagator to replace the delta function equation. That's why we get D12. Now, for the other terms, we can work out explicit. For instance, I can, as said, I can again do the replacement, but now for the phi2. Okay, I can replace phi2 by y. The payment is actually by box y y2. Okay. The reason is the same as before, right? I just iteratively used a rule, which is still true for interacting case. I can get this one. Now up to here, then again, the result coming out of this calculation, then we get this step. Now for this step, I explained this term we can stop temporarily because we already get the G square factor together with some kind of correlation function. In the perturbative, for perturbative purpose, if you only want to compute your result up to G square order, we can safely approximate this remaining correlation function by free series result. Is that clear? The reason is because otherwise you will get more coupling here, which is give you higher orders, but for those higher orders you don't care. So right, so you only care the G square orders, which means you can approximate this by free series. So what is the free series result for this object? We have here, right? We just work it out. We prepare the root. We have most general for insertions result is given by these three terms. You see. Now we just we need the special case, which is the 2 points coincide at x and the other 2 points coincide at y. Okay. Which means you can do whatever you want. You can say put the 1, 2 coincide. Okay. Or 3, 4 coincide. You can get the results. You see. So since this is it may easily confusing. Write all the steps. Now I erase this crucial equation. You should keep in mind. Okay. So basically, 5x, 5y, 5y, as said, this is a short notation following precisely the same rules here. Just put 2 points on top of each other. You will get the dxx. Okay, you see, it's a little bit funny, right? You get the two same points dxx. Okay, it means what? It means some propagator. It comes out, but it comes back again. Okay? Such kind of propagator, you see? It comes out and turns back. Come back. Now, there is a dyy plus twice dxy squared. And there are, of course, higher orders, but we don't quite care. As said, in principle, if you view this as interactive, okay? There may be some higher term, but we only want to pick up the leading order for free series. Always keep in mind G is small. Okay, always keep in mind G is small, so I can throw away lower higher G orders. Only keep this leading order. Now, what about we don't forget we have another term. 2 pieces, right? There's another term here. So what about these other terms? So the other terms, we just play the game once again. Keep in mind that the other term in front, there is already one coupling factor, G. Okay? There is already a G here, which means that we should work out this one. Of course, in general, again, this bracket means for the interacting theory. There could be contain many couplings, okay? Many coupling different terms. But keep in mind, since we already have a G there, we only need to work up to the G squared. We can stop. So let's do it. So again, use the tree. Let's repeatedly use the tree. This will be this E, X, Y, X, Y, Y, and okay. Again, you use the trick derived there for the interaction case. Now E, Y, E, X, Y, Y. Clear? We replace up to here. This step we already clarified, okay? How to get this one, both for free and for interacting. Now, in the interacting case, the difference now, you have to replace both by squared because this series is interacting, right? Now you see, now I get it. Once you replace by using the interacting theory equation motion, you will have one more factor of G coupling. You see, I'll get another G. See, this essentially means I can approximate the remaining, again, correlators by free theory result because G is always small. See? Because there's a G, this is a G, there's another G, already G squared, right? If you have one G squared as a factor, or others can be approximated by free theory. So what? So if you realize that, then this is nothing but E, X, Y, E, Y, Y. But there are some higher orders, but we don't care. There are some G squared order terms. We ignore those. Okay. So in this case, we also work out this second piece. We have three pieces. You see, we explicitly work out the three pieces. Okay. Maybe it's interesting to pause a little bit because this is not quite usual. You know, this is just a simple one-point function. You see, maybe it's worth to discuss a little bit how to understand this one-point function. For example, this is the one-point function. So a question you can ask: what is the difference between free theory and interacting theory? Okay. For free theory, what is the result of this one-point function? Can you guess? Can you guess? Well, you can view, if you have interacting theory, you can have continuous coupling. You can view the free theory as your limit. Which limit? Correct. G goes to 0 is the free theory limit. Then we know this is the result of that one-point function. If you just check it, just guess it, you will immediately take a G goes to 0. Okay, keep all other fixed, then you'll get 0, right? So this kind of one-point function in the free theory case is 0, but in interacting case it's not there. You can see it's missing. This is the difference. Now, this is the remark. Now, put everything together. Now it's time to put everything together. We will get the final result about the interacting theory. 2-point function phi 1, phi 2 will be equals to, as said, there are few pieces. From that line, we can see there are 3 terms. Now we work out everything explicitly. We realize that both this term and this term, we can work out up to G square order. Okay. Then put everything together. Since both second and third term are G square order, we just put them together. And package everything together. Okay. That clear? Just plug in both this result and this result into this equation. You see? Just write all the D explicitly. You get this one. You clear? There's no mysterious here. It's just a simple exercise. And you just stay there and work it out. Okay? There's no mysterious. So this is the perturbative result up to G square order for the interacting theory 2-point function, time ordered. Okay. As we emphasized, the result is expressed in terms of D. Okay, while D is defined for free theory. Okay, that's the point. Don't confuse yourself. So in this sense, this is really a perturbative expression, meaning that we try to standing on the free theory. Okay, just do a little bit of massage or deformation, try to approximate the interacting theory. That's the spirit. Okay, it's not an exact result. It's not an exact result. Okay. In contrast with the earlier Schwinger-Dyson equation, as we emphasized, Schwinger-Dyson equation itself is completely non-perturbative. Okay. There's no confusion. But for this result, we only claim that this is a perturbative result up to G square order. Now it's interesting, right? Since you get some kind of funny, interesting structure in this way, you can try to, again, pictureize, like what we did for the free theory. The free theory, we get such kind of structure, we can just pictureize it using a diagram to represent it, okay? Represent it. We can do the same thing here. Yeah. Just directly draw here. So for this part, we can use a diagram to see just the 2 dots with a line connecting. For this one, we can use so this is 1x, x, y, and y2. We can use this dot. Space limit. So this is a free propagator that's claimed there. It's plus some G square times something, but that's something. Let's also draw it picture-wise. This is x1, this is x, this is y, this is x2, plus this is x1, this is y, this is x2, plus This is x1. This is x. This is x2. But now it emerges with a bubble. And this point is y. Okay? You can realize that this is really an intrinsic picture corresponding to the formula here. You see? Well, this is a propagator from 1 means x1, okay? From 1 to x, okay? X means x, 1 means x1, according to my notation, see? From 1 to x, this is the second term, right? The first term is the straight line, from x1 to x2. This is from x1 to x. Now, times another from x to y, you see? But there are square, meaning there are two propagators combined together. Okay? There are two lines from x to y. Now times another from y to x2, which is essentially this diagram. You see? Okay. I just try to using another easier picture-wise, intuitive picture to represent that formula. But you can just think these two things are just equal. Okay. The representation is different, right? But the thing is the same. And for the second term, we have from x1 to x, and then x to x. Okay, x to x means what? As we explained, from the point, then your propagator turn back to the same point. You can only draw such kind of diagram. You see? So that's the part here, the third diagram. And then y to y, right? And y to x. So for this diagram, a little bit disconnected, you see? Disconnected. So for this kind of diagram, we call it a connected diagram. For this kind of diagram is disconnected diagram. Now the last one, let's try to understand. It's from x1 to x, and there is another x2 to x. Meaning the x line here, x2 there, they meet at the same x point, right? Right? So basically, D is we always use a line to represent a D, but we carefully pay attention to different positions, which one is touched to which. Okay, just draw it. You can get that diagram. Easy, unique way. There's no confusion here. Okay, no mysterious here. You see, now here there is the x, y. Means x2, x, y, and 2 they meet at x, and then emerge. The x will again propagate to another y. Okay. Now together with another y to y, this is just another one. There's a bubble. Because y to y is only possible to represent this figure. So this is the last. This is the last. To meet together to y to x, and then to y, propagate to y. Okay, and then times the y come to the surf. So we get this diagram. So this is the famous, if you want, this is the famous Feynman rules, the Feynman diagram. Feynman rules to represent the position space correlation function. Okay, or this is, you can call this is the position space Feynman diagram. Position space means you really the operator really located at the space time. Okay, it's not a momentum space, but position space. You can use the Feynman diagram to represent the correlation function in the position space. Yeah. It's not difficult at all, right? All the steps, as you can see. There's no mysterious to derive this Feynman diagram. You can just easily training yourself, okay? Training yourself to work out another exercise. For example, lambda 5-4. You can do it straightforward. You can even go higher point function. For instance, go 4-point function. You also get this beautiful structure. You can draw the beautiful diagram. But if this is your first time to see such kind of thing, we have to pay a little bit time to really make the Feynman rules more sharp and explicitly, we should build up, in principle, we should build up the Feynman rules clearly. So what is the rules? What are the Feynman rules? We call it the rules, but what is the rules, right? What is the rules? So let's state, since this is important, let's just, I already explained everything basically, but now let's using words to represent what I said. The rule is going to step 1. Start with points. This is the Feynman rules. Start with points xi for which correlation function is measured. This essentially means that if you want to compute a correlation function about this kind of insertions, you should start with those insertion positions, which is xi. Okay. Now start with this point and do what? You start to draw, right? Now by the rules, what we want to say, what we mean is that first you give me a definition, or you give me a definition for the object I want to compute. We want to compute. Now I want to save save my time and just want to try to directly write down the result without this tedious calculation. What can I do? If there is a diagram or picture one-to-one corresponding to the formula, I can just try to draw the pictures, draw all the diagrams, and then follow the diagrams. I just immediately write down the final result. I don't need to calculate. Okay. That's the idea. So that's the reason why we care about these rules. Now you start with these points, and then you start to draw a line from each point. The rule is about, say, a line can either contract to an existing line given Feynman propagator, which is D, okay? Or it can split according to the interaction. So what does this mean? Let me try to according to the figure, I can explain what this rule means. It just says that, okay, starting from some lines, okay? You start from some lines, you start to draw. If there is some other lines, you can just contract it to form a propagator in this way, you see? This is just a simple propagator. Just contract them or connect it together. It's fine. You can also split, meaning that you start from a line. You're starting from a line, but you can split at some point, you see? If the theory allowed the interaction, for example, such kind of interaction as this example shows, if there's a phi qubit interaction, essentially it allows some such kind of 3 vertex, you see? Because there's a phi qubit. The reason why we can draw such kind of structure here is essentially because there's a phi qubit, okay? Is that clear? You can imagine if there's a phi particle, okay, just very roughly, okay. If there is a phi or field, because you allow that there's a phi qubit coupling, in the equation motion level, it essentially means the box acting on phi will be equal to something with phi square, which essentially means the propagating of phi can create or generate some other phi squares. You see, it's essentially this structure. You see, if there is a phi, you can split into 2 phi. Okay, you see, that's because of the interaction. Yeah, that's what the rule says. Now each split gives a vortex with the coefficient of L prime interact prime phi times I factor I. This means what? I'm trying to set down the rules, and just following the rules, you can easily write down the final result without explicit calculation. So I specify everything, including the coefficient. So if you have a vortex, you should always contribute a coefficient like this one. So in the phi cubic case, this is nothing but g over 2, right? G over 2, now times I, in I. Okay. Now the rule number 3. We should sum of all diagrams with all lines contracted all internal, we can also have internal lines, right? Clearly. Internal lines, also internal vortex. Internal vortex just means this kind of vortex positions. The position which you can split, okay? Which you can split. So this I have to call the internal vortex. This one. With all the internal vortex integrated over. It means what? It just means this integral over x and y. You see? Okay? I use such kind of diagram to represent this final result. I have to integrate over x and y. As you can check, all this x and y in that diagram is the internal vortex. Okay? It's the internal vortex. Now, rule number 3. We should drop all the n factorial factor in the coefficient of the interaction. But divide by so-called something called symmetry factor, geometric symmetry factor. For each diagram. Yeah. So this last step leads a little bit of consideration or analysis. It's not obviously why, but here let me try to explain it in some simple way, okay, intuitive way. So what the last step says that in the step 2, number 2, we mentioned each vortex will contribute a coefficient of that interacting coupling term. You see, right? But now we emphasize we shouldn't care much about this n factorial. The reason is because we defined this L interact using this kind of factorial. Okay. See, if the interaction is 5 to the qubit, I use the 3 factorial here in front. Some normalized factor. You can think in that way. But the point is to establish, to follow the Feynman rule for some figure. If you want to write down the result, you shouldn't care that 3 factorial. That's what rule number 4 says. Okay. But then what? You have to do something, right? If you don't do that, so you need, first of all, you need some reason. Second, what is the complete result? Complete result is you. Basically says you can ignore this one. This is not ignorance. It is essentially because some other counting factors were cancelled with this initial n factorial. That's why we should drop it. But now, if you simply do that, again, it's not correct. It's not fully correct, completely correct. You have to worry about something more. Yeah. The thing is you have to divide it by some geometric symmetry factor. Okay, let me use this example to explain what this last step really means. As we can see here, even though the L interacting prime has a G over 2, you see. In the Lagrangian, this is this factor. In the once you take prime, this is G over 2, you see. But now, in order to establish the final result, first of all, I don't care whether it's the 3 factorial or 2 factorial. I ignore those. I just write a G. For each vertex, I just write a G. Because all the diagrams have 2 vertices, you see? So you see? For each vertex, I just write a G following the rules. And this G times an I, right? So there is IG. IG squared, I get a minus G squared. See? That's why I get a minus G squared over there. Here. You see? So this minus G squared just always coming from the rules, you see? But as I said, the last step suggests in order to get the final correct result, you have to divide something. This kind of 2, 4, or 2 factor. This kind of factor is called the geometric symmetry factor. Okay? If you carefully divide those geometric symmetry factor, then you can get the correct result. I just try to consistently convince you this result really can be obtained by all these following Feynman rules. I haven't explained what is geometric symmetry factor, but just following the rules, get this result. Is this rule clear? Are there any questions for the rules? It's clear, right? You should know what I mean, right? I just finally just explained all those steps. Then basically, if I hand you a diagram, you should write down the result. You see? You should immediately write down the result. Yes? By knowing this theory, right? You should immediately write down the final result. Now, then you may keep asking, then you just tell me the rules, but you didn't explain how to derive these rules. It looks a little mysterious. But let me explain why we should do such kind of thing here. And what is the geometric symmetry factor? This factor comes from some overcounting. Let me explain by taking one graph. So you may wonder why we should care so much about and what is this mysterious factor. The factor can be worked out. Yeah, it's not a big deal. It's not first of all, it's not some very subtle and deep. It's not like that. It's just a simple one. So where it comes from? So think about this diagram. Let's take this as an example, right? If you know for one diagram, you will know everything, right? Because you know where it comes from. So if you think carefully about this diagram, you might immediately realize that because as explained by the rules, the bigger concept here is the contraction. Whenever you have a big diagram, you can always decompose it as some minimal elementary building blocks. Try to contract to form a big diagram, right? That's one way to think about whatever complicated diagram, right? So in this point of view, you can decompose all the diagrams into some elementary building blocks. Okay. For instance, you can just you can decompose them to use this kind of building blocks. Okay. And this kind of building blocks in something like this, and then you can try to contract them. Okay. Contract means just fuse. Okay. Connected together. That means contract. Right? That's really the meaning of such kind of diagram. Actually, the factor comes from this contraction. The factor comes from contraction. Now, again, as said before, if you have such kind of vertex, it essentially means there is a 3 phi x standing at the same point, okay, which is prepared for your contraction. Is that clear? Because you have 3 vertex, right? If you're using the diagram completely using the contraction to understand this diagram, you should think about at the vertex there are 3 phis, okay? There are 3 phis standing there. They are prepared for your whatever contraction. So there are 3 phis here, and similar way there are 3 phi y. Okay, and let's say there is a phi x2. I'm now trying to. Because now the geometric symmetry factor somehow looks a little bit mysterious if you're just looking at this figure. I'm trying to use an algebraic way to explain. That's very simple to explain how to get the symmetry factor. And this way, there is another phi xy. You see? So there are such kind of operators here. Now you just do your contraction. You see? You do your contraction. Starting from there, you have no choice, right? You have to start from there. This is by the rules, right? Or you try to contract. Now there are 3 same phis. So if you're counting, you have 3 choices, right? Right? So here, there's a 3. Okay. Remember that there's a 3. You have 3 choices here. Is that clear? Now after you fix one of the 3 by the contraction, you can do the remaining job this way, right? For instance, now you have only two choices, right, for the remaining phi x, because so you have 2 choices. So there is a factor 2 here. Now pick phi x, and then have to contract with another phi y, right? You see, right? Now you have to contract with a phi y, but as said again, you have 3 choices. You see, because there's 3 phi y, right? Those 3 choices. Now there's another one. You don't have remaining choice here, right? Because there's only 1 remaining. But you still have 2 choices for the other phi y. Okay. So lastly, you don't have whatever choice here. There's only 1 contraction. So you see. Using contraction, we can simply counting this how many factors coming from the permutation contracted with which one. There are different choices. We can count in this multiply factor out of this contraction. You see, easily. Now, if you are a careful person, you immediately realize that if I count in this way, I did a little bit of overcounting. Is that clear? Anyone realize that? I did overcounting, you see? Which overcounting? Because some, you see, when I counting, see there is a factor 3 here, which essentially means, right, I already counted attached to some other phis, okay? That clear? But later I counted for the other files, because this X and Y, this line and this line are the symmetric. Some of the counting is actually the same, in the same contraction. Yeah, it's not difficult. You just check it carefully. You realize, for instance, you can just stupidly write all the contractions explicitly. You realize, okay, this and this are just coincide. This means there's overcounting. So precisely the so-called geometric symmetry factor is coming from the overcounting. You have twice overcounting, you have two geometric symmetry factor 2. You have 3 times overcounting, this will be 3. That's the reason we have to divide. You see, we have to divide. Okay, we have to divide by this kind of factors. Now you ask me, what about this not overcounting factors, right? So clearly it suggests that there are some factors you have to times. You have to multiply those factors in order to get the correct result. Because all the different correct contractions contribute to the amplitude or coordinate functions, right? Now that non-overcounting factor is what? You see, you can immediately see this kind of factor is precisely, if you first ignore the overcounting, this 3 times 2, 3 times 2 precisely cancelled with the Lagrangian 3 factorial, right? Because you have 2 vertex, then you have 2, 3 factorial. 2, 3 factorial precisely cancel this factor. I just counted, right? If you are a sloopy person, then it's finished. But I said it's not entirely correct because you did overcounting. That's why we have to divide by this geometric symmetry factor, which essentially comes from the overcounting. Okay? If you don't do the exercise, it may be still a little bit mysterious to you, but I strongly suggest you just do it yourself. It's not mysterious at all. Okay? The key point is that this kind of factor comes from the overcounting. Okay? If you ignore this overcounting, the multiply factor precisely cancels this n factorial factor. Okay. So that's the point. So what's time? So up to now, by following those rules, basically, you can follow the rules. First, draw the diagrams, and then following the diagram, write down the result without explicit calculation. Okay. So, yeah. So I think you should do your homework. Say for lambda phi 4, do the same exercise. And counting all these factors correctly. Do you have any questions? Okay. In the last 20 minutes, we are going to move to the. This is called the position space Feynman diagrams or Feynman rules. Now we want to move to the momentum space. Because as promised, we want to really build up the relation with S matrix elements or the scattering amplitude. So how to connect such kind of time-ordered correlated result with this scattering amplitude. Yeah, this is the next step. By the way, there are different, let's say, some different interpretations about this one. The way I suggest, I think is more, it's more clear way. But you can, if you read the textbooks, for instance, Paskin, they'll just tell you, you can think about this kind of geometric symmetry factor. For instance, for this diagram, is about the permute these 2 lines. Okay, because if you permute these 2 lines, these are the same diagram. Okay, so that 2 factor is coming from here. Now for this diagram, again, you can permute this one and this one. and also this one and this one. So you have 4 factor over counting, or you have to divide it by 4. Okay. Now for this diagram, just following, there's 2, right? Because here you can permute this line and this line. It's still the same diagram. So you have to divide it by 2. There are different ways to understand it. But sometimes people may be getting confused. Yeah. But it's not mysterious at all. So if you just do it carefully, everything is clear. So we want to try to see what happens if I switch to the momentum space. This is the so-called momentum space Feynman rules, right? Of course, in order to establish this momentum space Feynman rules, we have to go step by step. For instance, let's denote T1 as the second diagram here. This diagram. Okay. If I denote this diagram as it's labeled as T1. T1 is equal to this diagram, which is x1. Let me draw it again. It's basically 2x, and then 2y, and then 2x2. Okay. Now, following the rules, we have already know the result. But just following the rules, this diagram will be given by ig squared, which becomes minus t squared. Okay. Following Feynman rules, write down the result, and divided by the symmetry factor, which is 2 in this case. This is the coefficient. Now, integral over all the internal vortex, x and y. Now, multiply all the propagators represented by this diagram. Okay? Okay? From 1 to x, x to y, then 2x to y. So all the relation is about the multiplying square. Finally, dy2. dy2. Okay, this is the result. Of course, we already know the result. Just repeat it again. The point is now I can do Fourier expansion. What if I do Fourier expansion for all the propagators? For instance, Fourier expansion essentially can be done this way. For instance, dxy, I can write it as the p-space integral divided by 2 pi to the 4th with an I over p squared plus pi epsilon exponential ip xy. Right? This is what we learned. This is what we learned 2 weeks ago, right? 2 weeks ago, right? We already know this is correct, right? We spend a lot of time to try to introduce control integral. We go very slowly to emphasize the important. Yeah. Okay. So this is already know. The point is there are many D's, right? You see? But whatever it is, they are the same type, okay? I can Fourier expansion all the D's. I can Fourier expansion in this way, all the D's. This xy can be generally means 1 xy or 2. Okay? Just following the same expansion. Okay. Get the final result. So if you employ this, try to use this one, do the Fourier expansion, what you can get is the normal formula here. What can I do? So after Fourier expansion, this T1 becomes minus d squared over 2 dx integral dy integral. And there are many p's, right? If for each d, we do the Fourier expansion, right? So we get dp1, dp2, dp3, and then dp4. And all these different p means the momentum associated with the propagator. Okay. See, for example, p1 is the associated momentum for x1 minus x, okay, which is essentially coming from d1x. Okay. Now exponential ip2, which is associated with y minus x2, momentum associated with this one. And of course, on physics, there is a times e to the ip3, which is associated with x minus y. There is also a e ip4, which is associated with. I think I need a typo here. Yeah, it's okay. There are two x minus y, so we have to do two Fourier expansion. Then we get the 2 and all the propagators turns out to be this form. Okay, I didn't do much, but just the Fourier expansion, my T1. It's just that diagram result. Okay. See, if you're familiar with Fourier expansion, it's trivial, right? Now, as always, once you Fourier decompose something, you know, to keep in mind, you need to exchange the order of the integral. Okay. I can perform the xy integral first. Okay? I can perform the xy integral first. So the integral over x will give you a delta function. I can easily count, right? You see? All these structures has nothing to do with x and y, you see? It's just all about the p's. So all the x and y integrals is about such kind of exponential IPX. Okay? So this kind of integral gives you what? Delta function by definition. Okay? So this gives a delta function 1 minus p1 plus p3 plus p4. This is a result of the x integral. And what about y? Y integral similarly will give you p2 minus p3 minus p4. Okay. Is that clear? Now we can integrate over P3. Okay? Once you have such kind of delta function insertions, I can try to integrate over P3. Why? Because integral over P3 will kill one's delta function. Okay? Once you have delta function, you can try to integrate over some variable inside, contained in the delta function variable. Okay? Then it will kill the delta function, right? That's the definition of delta function. But not both, right? Now you have two, okay? So how to deal with such kind of two delta function, both rely on the P3? Well, just do step by step. Just kill these ones and then set a constraint, right? Set a constraint. The constraint will be the P3 equals to P. For instance, I kill this delta function, will set the constraint P3 equals to P1 minus P4, right? Now you just plug in this constraint to replace this P3. It's done, okay? So that means this delta function will become the delta function of the P1 minus P2. Okay? That clear? This is the way I deal with these two delta functions. Then eventually I change the variable. Just I don't like this P4 because many P's are already integrated over. There's only P4 left over. I switch this P4 notation to K. Okay? I change the notation. I see these steps in words, but it's a very simple exercise, right? I don't want to write long formulas. But after you perform all these steps, you can get another slightly simple result. Which is T1 now becomes, after all these calculations, it becomes a decay integral. There is a P1 left over, of course, we haven't integrated out over. And there's another P2. And there is an exponential IP1x, there is an exponential minus IP2. X2, and then times all these momentum space propagators. As you can see, I ignored the mass square terms in order to brief the formulas. It doesn't matter, okay? This is what you get. Okay, as you can see, just simply doing these integrals. First the Fourier expand them, and then do the xy integrals, and then do the P3 integrals. And then carefully deal with the delta function insertion. Change the P4 to K. This is what you get. This is the result, what you get. Now, it's not finished yet. This is the partial result. But in order to truly establish this result, with the S matrix element, we have to use the LSD formula, which I leave you to derive it, prove it, okay? So by following LSD, let me write the formula explicitly here, which is nothing but in this case, if you still remember that in the LSD formula, there is a there are many big factors in front, okay, in front of the time ordered correlator in order to collect with the S matrix element, okay? See, now I write it just simply, we know there is a Fourier transformation called Kerner, okay? But together with the momentum square. Now I just write it as a momentum square. It's equivalent to the box, okay? Now times the time ordered correlation function for the interacting theory. This is the LSD, okay? I simplify the LSD a little bit. Why? Because now I only want to deal with such kind of super simple diagram. Okay? As you can see, there's only two external points, x1 and x2. In order to connect such simple diagram to S matrix element, essentially means there are only two momentum, which one is input, another is output. Okay? You can choose to translate this one to the scatter amplitude. You see? I choose in this case, I choose a pi as my input momentum. This is times with x1, okay? Combined with the x1. And the pf, which is my final momentum, times with x2, okay? These are two Fourier transformations. This is the pi squared. This is pf squared. Now this times the time order the correlator will give the X matrix element. Okay, this is the LSD in this for this simple diagram. But you should notice that yeah, the pi and the pf is what we choose. Okay, it's not something you should keep in mind clearly. Okay, pi and the pf is what we choose to set the scattering experiment. Is the parameter we choose. Now, following this formula, you just plug in. Now we have the result for this one, right? We have the result for this one. Sorry, I didn't finish. There's two factors I missed. Lastly, there's third function of P1 and P2. Then is a complete result for the time order correlating function. Now you just plug in this T1 into here, because here is what we want. Okay, this part is what we want. Let's replace this by T1 and then do this Fourier transformation. You get the precise explicit S matrix element. So what is that? So if you do it carefully, you can immediately realize that even though there are like three integrals, but it's actually very simple. Meaning that you realize if you realize something simple, which is I can first perform the x1 integral. Okay, I can first perform x1 integral. If I do x1 integral, what I get is 2 pi to the fourth, a delta function p1 minus pi. Is that clear? Just plug in these results into here. Right? Deal with the integrals. But the point is, all these integrals looks complicated, but it's actually very simple. For instance, you can first perform the x1 integral. Let's count. For the x1 is only combined with pi. x1 is only combined with p1, right? So there's pi minus p1. Third function, pi minus p1. You see? What do you get? Now, similarly, for the x2 integral, you can get 2 pi to the fourth delta function of p2 minus pf. Okay? It just says that the x1, x2 integrals impose the condition that match the p1 as the initial momentum and the p2 as the final momentum. You see? Now, if you realize this, then there is the P1, P2 integral, and you can easily perform. Okay, because now you have delta functions. You see, these delta functions I can perform the integral over P1 and P2. As I said, it's just set P1 equals to Pi, P2 equals to P. Okay. So all these 4 integrals already can be finished, can be done easily. X1 integral, X2 integral, P1 integral, P2 integral. Only left integral is K. Okay. So the final result is very simple. It's just about the integral about K. So let me just show you the final result. So finally, this this one will be minus G2 over 2. It's only about a single integral about K. Times I, P, I minus K squared plus I epsilon times I over K squared plus I epsilon. And times 2 pi to the fourth. And third function fourth P I minus P F. Okay? Is that clear? Because there's another delta function here. There's a physical meaning for this one. Because now if you perform the integral over P1 and P2, just set this value to Pi and this to Pf, okay? And as I said, it can only triggers once delta function, not twice, okay? So there is a one delta function remained, which looks like this one. Clearly has a sharp physical meaning here, right? It's just about the momentum is conserved, okay? So whatever momentum in input is equal to the output momentum. So this is the final result. Yeah, we don't have time today, but just to explain a little bit. So this result again, this result, let me just try to associate this result with this diagram directly, okay? Again, if I don't want to do the tedious calculation, this is like many integrals for delta functions, I just want to read off the final result from these diagrams. What can I do? It's actually, it can be done, right? It can be done easily. You see? Simply, this means there's a k integral. There's a k integral. There's a, as said, there is a pi. For instance, there's a pi input momentum. Let's say if this is the input momentum coming this way, okay? Okay? Now it is split into two. If you set this is k, then this left will be pi minus k. Okay? Now they meet together. Since pi equals to pf, so it's, again, it doesn't matter if you look by pi or pf, it's okay. Okay? So you can actually associate this momentum to this diagram and then understand this result. And you can try to even establish the so-called momentum space Feynman rules, just like what we did before for position space. We don't need to do this intermediate calculation. Let's say, let's counting. So since there is a k is a free momentum k, so k has to be integrated over, right? Laterally. Now these two p's, like two propagators. So one propagator comes from pi minus k, you see? As I denoted here. Another propagator is coming from the k, it's here, right? See? There are two propagators in momentum space. Now, compared with the position space structure, clearly we throw away these external lines, okay? We don't assign any structure to the external lines, as you can see from here, okay? Because this G square, as before, we can consider coming from the vertex, okay? Now these two propagators only coming from the internal lines, okay? Now this delta function is only about the physical conservation of momentum. So all the final result can be clearly assigned to this diagram, okay? Slightly different from position space Feynman diagram. But it's actually even simple, right? If you might realize. If you want to directly write down the S matrix amplitude, or sorry, matrix element or S matrix result, or from this diagram, you can just do it that way, as I said. This is the momentum space Feynman rules, or how to connect the time order correlator for a particular diagram to a S matrix. Okay. Yeah, let's stop here.